Let's apply what we know about how an impulse can change linear momentum to a problem in which we have two fish. We have fish P and we have fish Q. And fish Q is moving at a constant velocity that's observed in the inertial reference frame. So it's Q with respect to O. And fish P is moving at P with respect to O. And fish P wants to align its velocity in the direction of fish Q. Now, from the perspective of fish P, as it observes fish Q, it can only observe the relative velocity, so the velocity of Q with respect to P, and it's observed in its own reference frame, so it's reference frame B. And so this is a path frame that's drawn on the fish P. So to align its velocity with fish Q, fish P has to apply an impulse with its tail by beating against the water, and that's going to change both its direction and its speed. And our job is to calculate that impulse. So what the fish P can observe is the velocity of Q with respect to itself, and it's making the observation in the B frame. Now, it's important to note here that between each tail beat, that the fish will glide with a constant velocity. And so anytime you hear the idea of moving at a constant velocity, your ears should perk up because you know about Newtonian relativity, because anything that moves with a constant velocity is also an inertial reference frame. So that means that the velocity of Q with respect to P as observed in the B frame is the same as the velocity of Q with respect to P in the inertial reference frame. And so we can link these back to point O, which is fixed in the inertial reference frame, with the relationship that velocity of Q with respect to O is equal to the velocity of P with respect to O plus the velocity of Q with respect to P. Now let's not forget what we're after here. We want the velocity of fish P with respect to O to equal to the velocity of Q with respect to O as observed in the inertial reference frame. The whole idea is to align the fish and its speed with fish Q. So if we consider this problem as between a time 1 and time 2, time 1 in which the fish are out of sync and then time 2 in which they are in sync, then what makes that change is an impulse, so Fp from time 1 to time 2. And so now we're set up perfectly for the linear momentum impulse problem, in which we have the mass of P multiplied times the velocity of P with respect to 0 as observed in the inertial reference frame. So this is our linear momentum, and this is at time 1. We want to add the impulse from time 1 to time 2, and then this is going to give us the linear momentum, which is the mass of P, and this would be P with respect to O as observed in the inertial reference frame at time 2. Now remember, we said that we want our velocity of P with respect to O to be the same as Q with respect to O. So that means that we can just substitute the velocity of Q with respect to O into this equation. And we can specifically say that it's the velocity of Q with respect to O at time 1. Because when fish P was observing fish Q and desiring to match its speed, it was at time 1. It was prior to the impulse that it was going to apply. So now that we have our new expression, let's rearrange our terms and solve for the impulse from T1 to T2. And so here we get the expression for the impulse from T1 to T2 that fish P is going to apply, equal to the mass of fish P multiplied times the difference between the velocity at Q at time 1 and the velocity of P at time 1. And so we can make a substitution here where what's inside of the parentheses is the velocity of Q with respect to P as observed in the inertial reference frame, and that's the observation made at time 1. And so then we've solved for the impulse that fish P needs to apply, and that's simply equal to the mass of fish P multiplied times the velocity of Q with respect to P at time 1 as observed in the inertial reference frame. And remember that the inertial reference frame in this case is actually the same as the B frame. Because the B frame which is the path frame attached to fish P, is an inertial reference frame in between tail beats. So what's great about the solution is that we see that the fish P only has to make this impulse based on its own observations. So its observation was the velocity of fish Q with respect to itself observed in this frame. And so then the impulse is a multiplication of its own mass and that velocity. And so if it can generate that impulse, it simply needs to make that impulse in the correct direction, and then it's going to change both its orientation, so to match the direction of fish Q, but it's also going to be able to match the speed in that direction.